The electrical conductivity of materials spans more than 25 orders of magnitude, making it the largest variation of any physical property of materials. We have quartz here on the left, which is a particularly poor conductor of electricity. We have silver here on the right, which is one of the best conductors of electricity. Electrical conductivity is denoted by the Greek letter sigma and has units of inverse ohm meter. With the conductors over here on the right and the insulators here on the left, it's tempting to call this middle regime here semiconductors. However, we have to use this word with care because semiconductors refers to a specific set of materials, such as silicon, such as germanium. Water most definitely is not a semiconductor. With semiconductors, we can dope them with impurities to make them highly conductive in certain areas. Semiconductors also tend to have long-range order and can even be monocrystalline, and their conductivity actually goes up when they're heated. But the basic question is really, what is it about insulators that make them such poor conductors of electricity, and why are metals such great conductors? Well, if we look at this cartoon where we apply a positive bias across this bar, in this case we have a positive lead on the right attracting electrons from left to right. We can imagine that the current would be higher for this sample if we have more electrons participating in the flow. That is, the higher the current, that corresponds to a more conductive material. And if we look at metallic bonding, we see that we have valence electrons that are not tightly tied to their atomic cores. These valence electrons, which are blue dots in this cartoon, are free to move when we apply a positive bias. They're not really bound to any atomic core. So as we apply a positive bias, they move from on the right. They would move from left to right. And for the current to continue, of course, we would have to have electrons replenishing from the left. Otherwise, we would set up a positive bias here, which would stop the current flow. We contrast this with quartz, which is, again, one of the best insulators. And in this case, the valence electrons are participating in bonds, and they're not free to move. So we have a dearth of electrons, of free electrons, that can participate in flow. Now, I do want to say something about metals. It turns out that in metals you'll have scattering, which can compromise the conductivity of the material. So I have circles here representing atoms, and we have a nice registry here. But there's a grain boundary where there's a neighboring grain, and actually most metals that you encounter have grains. They're not monocrystalline, where they would all have where you'd have the same registry across the material, but they're actually grains in the metals that we usually see, and that represents a change in orientation. And this grain boundary would actually serve to scatter electrons. So we have an electron cruising from the left to the right here. It would actually bounce off this grain boundary and scatter around before eventually making its way to the right. Another source of scattering can be an impurity or precipitate, so an electron can bounce off of that. Another source of scattering is vibration, which are phonons. So if we heat up a metal sample, the amplitude of vibration would increase, which would basically increase the scattering cross section in the electron. So when we heat up metals, in contrast to semiconductors, when we heat up metals, the conductivity actually goes down. I'll just show this very quickly. A polymeric structure basically looks like spaghetti, where you have these long polymer chains which twist and turn, and you can imagine that this would actually be a source of a lot of scattering, and most polymers by their nature do not have electrons to spare for conduction, at least not many of them for electron flow. So that's two strikes against polymers in general when it comes to conductivity. A word should be said about conductivity and resistivity. Conductivity is denoted by the Greek letter sigma, as mentioned earlier. Resistivity is denoted by the Greek letter rho. Conductivity and resistivity are inverses of each other. And the units of conductivity are Siemens per meter, and as I mentioned before, that would also be inverse ohm meter. It's emphasized here that conductivity and resistivity are intrinsic properties. That is, an intrinsic property is inherent to the material itself, regardless of the size of the sample. So an example of an intrinsic property would be density, or even reflectivity or shininess of a material. If I have a small nugget of gold, it's shiny. If I have a huge chunk of gold, it's still shiny. But this contrasts to conductance and resistance, which do depend on the dimensions of the sample. And to help drive that home, I have a simple example here where we have the question, what is the resistance? Again, resistance would be an extrinsic property of gold wire with the following properties. We have the resistivity, 2.44 times 10 to the minus 8 ohm meters. The diameter of the wire is 2 millimeters, and the length is 10 centimeters. So what I do here is I have the resistance, that would be, again, extrinsic property, dependent on the resistivity times the length divided by the cross-sectional area of the wire. And I think that stands to reason. If you were to have a long, narrow straw, for example, the resistance to your breathing through the straw would be greater than if it were short and fat. So what I do is I just insert these values into the equation, and we have a resistance in the wire of 7.77 times 10 to the minus 4 ohms. And I want to finish this video with a bit of irony. So Siemens and Ohm are people. They were contemporaries back in Germany in the 1800s, and both in science and technology. And it turns out that they had also the same first name. They had the same first name of Ernst. So despite the similarities, that is, they were contemporaries, 1800s, Germany, science and technology, same first name. Today, at least in our minds anyway, they are more frequently remembered as being inverses of each other. Thank you for watching.